Hello, and welcome to our introduction to FidelityFX Super Resolution 2.0, presented by myself, Colin Riley of the Game Engineering Core Technology Group, and Thomas Arcilla of the Advanced Rendering Research Group. Before we get into our next generation of Super Resolution, we need to look back at what we achieved with FSR1. We released FSR1 in July 2021, and it is our high-quality, high-performance spatial upscaling solution aimed at being easy to integrate into game engines. As with most of our GPU Open releases, it is fully open source with a permissive license, and it has enjoyed great developer adoption. We have FSR1 available and coming soon in over 70 games, and the cross-platform focus has shone through with it deployed for PC, consoles, and mobile gaming. FSR1 has also seen uses elsewhere, like in our ray-traced hybrid reflections GPU Open sample, and it will feature in Radeon Super Resolution, which brings FSR1 to more games through driver integration. Despite the advantages, spatial upscalers have some limitations. FSR1 requires a high-quality anti-aliased source image as input. Lower upscale quality was tracked down to be caused by poor temporal anti-aliasing implementations many times. Quite some time had to be spent improving anti-aliasing before starting to consider the upscaling component. Additionally, upscaling quality is a function of the source resolution input. This was more apparent with the performance scaling preset, where artifacts such as shimmering and poor edge reconstruction could be seen. Which brings me to FidelityFX Super Resolution 2.0. FSR 2.0 is our next generation temporal upscaling solution, developed from the ground up after years of research. This is not built upon FSR1. It uses cutting-edge temporal algorithms to reconstruct fine detail and produces an anti-aliased output from an aliased input. The increase in quality over FSR1 is a significant leap, with different quality modes available such as ultra performance and support for dynamic resolution scaling. FSR 2.0 will be released on AMD GPU Open for cross-platform use, and it's highly optimized. Lastly, FSR 2.0 does not require machine learning hardware to achieve high-quality outputs, and implementations are provided via a library with full and open C++ and HLSL source code. Please let me introduce Thomas, who will lead you through the internals of FSR 2.0.
Thanks, Colin. So, as Colin explained, FSR2 is a temporal solution. This means that it produces high-quality upscale images from a sequence of low-resolution ones. So in this section, I will be presenting the internals of FSR2, and that presentation will detail the current state of FSR2 as of the time of this recording. And this might not be fully representative of the state as of today. So, while being more complex than FSR1, FSR2 still aims at being easy to integrate. It only requires 3 inputs at what I will be calling render resolution, and that's the low resolution game input. I will be talking about render size or low resolution for the input frames and display size or high resolution for the output upscale images. And to be more explicit, sequence of images is actually referring to a set of input image buffers. We purposefully kept this subset as small as possible, but some additional optional buffers may be exposed to help the algorithm later. The 3 required inputs are the color, that is expected to be jittered, and I will be detailing that after, the depth, preferably inverted and infinite, and the scene motion as a bunch of motion vectors creating pixels from the actual frame with the previous one. So now let's have a quick look inside the box to see how FSR2 is shaped up. So this is a representation of the inner structure of FSR2. It implements many steps that are required to produce a high-quality upscale image. So let's get a walk through the different stages of this pipeline. So FSR2 is a temporal upscaler, As such, we did start and build this upscaling technology on existing concepts from temporal anti-aliasing. So let me first expose those concepts. So given a set of input images, the intent is to generate a finer output resolution image by temporally aggregating samples. Though each of those images needs to bring new information in order to improve the final frame quality. And to create those slightly different images of the same view, the input image can be jittered. It means that when rendering the new image, camera is shifted a bit so that the generated image is containing some correlated but slightly different information. And this shift must be contained within a single input resolution pixel, the gray boxes on screen, so that this additional information can be correlated with previous images. You can see that each frame there on screen is adding a new sample to the pixel, and the more samples, the better the anti-aliasing quality will be. So for the aggregation to be valid, the jitter sequence must be providing an even distribution over space and time so that each input resolution pixel is fully covered when iterating the jitter sequence. So while the jitter sequence could be infinite, FSR2 is having some consideration about that sequence length when dealing with thin features, and I will be getting back to that topic later. So let's see how samples are contributing to the new frame. So each new frame will then be adding new information to the output image, but all samples are not having the same importance. And each sample contribution will actually depend on its offset location with regard to the target location. The closest it is, the higher importance it has by the time it is generated. And its age, newer samples are more relevant to the current accumulated frame. So what you can see on screen there is a pixel, the gray box, with its center in red. And two samples are represented there. The one coming from the frame n-1, close to the center, so high value by the time it was generated, but older now. And the one coming from frame n, further away, but still more recent. Let's see how we can formalize that contribution. So for each pixel, those samples S are merged using a simple linear interpolation with the existing accumulated color, the history H. The interpolation is done using the weight of the incoming sample and the total accumulated weight of the target pixel. So that's the alpha factor. So in this model, no matter its actual weight omega 0, the first sample S is fully contributing to the pixel. And when new samples are coming in, the relative weights of previous samples are adjusted so their normalized contribution gets to a total weight of 1. So this is how we compute the alpha factor. It's computed from the spatial weight omega from the new sample and relatively to the total weight tau of the already accumulated samples on the pixel. So one important point there, this method is actually not introducing any time-dependent variable. So we introduce that time dependency by capping tau to the expected weight of our target accumulated number of frames. So this is based on the average weight for each possible sample and the number of expected accumulated frame. And this very last number depends on the expected anti-aliasing quality. So that's the number of samples per pixel that we target. So now let's see how this weight is actually computed. So up to now, I did not mention low nor high resolution. So it's time to introduce upscaling to the picture. So in our case, the input image will be of a lower resolution compared to the output image. And to get the actual sample that will be accumulated, we compute an upsample value using the lens interpolation filter. So on this image, what you see there is the gray boxes that are the low resolution pixels with the blue dots that are the sample location inside this low resolution pixel. And in red are the centers of the high resolution pixels that we target. So for each high resolution sample P, we will use a 4x4 kernel of low resolution sample S. The image on screen is displaying a slightly smaller neighborhood for readability. So each low resolution sample weight is computing using ANSOS and the distance to the target high resolution sample. The final weight, capital omega, for the sample P is actually the sum of all the samples' weights, and the value of the final sample is the weighted sum of those samples with their weights. And that's using lengths can actually introduce ringing artifacts. And to remove those, we actually will be clamping P, so the final sample value, to the range given by the 2x2 centered samples of the 4x4 area that we are considering up front. So building up on that upsampling stage, we can now think of changing how Lancer's weight is computed to increase the sharpness. So we can increase the low resolution sample distance artificially by moving sample further away down the Lancer's curve. So compared to the previous frame, you can see that the curve has shrunk a bit. And it will basically decrease the importance of samples that are far away from the center and increase the importance of samples that are at the center. So that's how we do increase the sharpness there. So we introduce a new beta factor there, and that will then increase or decrease the importance of samples depending on how we treat that. And for now, this factor is updated using the luminance stability, local luminance stability, meaning that when an area of an image is stable, we afford some more sharpening there. So until now, this upscaling story has mostly assumed static images, where input samples are coherent from both a spatial and temporal perspective. And that's hardly representative of any games or computer-generated content. So to deal with animations, we rely on motion vectors. So that's one of the expected input of FSR2. Motion vectors describe how samples moved from the previous frame to the current one. And while we are getting jittered images, motion vectors are expected to have jitter-induced motion cancelled, meaning that on a still image, we obviously would expect motion vectors to be null vectors. Another point is that to correctly follow edges, it is common in temporal anti-aliasing solutions to use the nearest, depth-wise, the nearest motion vector. And this is referred as dilation. So what you see on screen there is two consecutive images, frame n-1 and n, and the two overlaid on the right picture, where we can see with the red arrows where the actual sample is, and the arrow is now pointing to where it was in the previous frame. So on motion then, the previous frame information that is referred to as history there then needs to be realigned with the actual frame. And this is done through reading a sample at its previous location based on the motion information and reprojected then at its new location. So this reprojection is again using lengths, and the ringing is as in the upsampling stage handled through a 2x2 kernel clamping. So there are still cases where the projection is failing. The history might not be correlated anymore with the new inputs. And this is the case when a part of the scene is disoccluded, for instance, or when shading changes occurs. So disocclusions have the advantage of having some geometrical support. On the other hand, shading changes are not supported by geometrical information, and they will be missing motion vectors and depth. That's, for instance, the case for lighting condition changes or animated textures. And in those cases, traces of the previous frames will be visible in the final accumulated frame. And this is commonly referred to as ghosting, as seen on this picture. So you can see indeed the previous locations, the previous position of the drone still being visible in the final frame. So let's see how we can address that. So the first case is disocclusion. So we do detect disocclusions by building a disocclusion mask. This mask is built out of depth comparison from the current frame and the previous frame reconstructed depth. It is a conservative test, relaxing comparisons to ensure jittered input does not create false disocclusions. So the three images that you can see there is again the motion between frame n-1 and n. And on the right hand side picture, you can see in black the areas that are actually revealed when the drone moves, and that's the disoccluded areas. So I mentioned reconstructed previous depth. Let's see how we build that. So To do so, we use the current frame depth. From the motion vectors, we are able to push depth samples to their location in the previous frame. The depth sample is then scattered onto 4 related samples in a bilinear way. This is the backward reprojection step. So multiple depth samples there will then hit the same location, and in this case, the nearest, meaning the depth-wise closest one, will be kept. And we do that using atomics on the GPU. So note that samples that are barely influencing, because too far from the scatter point, are not used. This selection is done through thresholding. So now we've got the two depths, the current depth and the previous reconstructed depth. So for each sample's depth, d, it is compared to the previous depth at the previous location on screen, and depending on it is closer or further, we can detect these occlusions. So this reconstructed depth is gathered in a bilinear way with the same threshold protection, so we don't take into account low importance depth sample. So this is the forward reprojection step. So to deal with depth buffer precision, the comparison is made using view space, using a minimum depth separation threshold based on some K-sep constants that I advise you to refer to the paper to get some more details about. Disocclusion is assumed when the depth difference is more than this threshold. So now we are detecting disocclusions, and we can think about fixing the history. But one note before we go forward with that. In FSR2, we only use input information to try and fix the history. Using existing accumulated information would defeat that purpose, in the sense that accumulated information would embed ghosting already, and that would defeat the purpose of rectification. So let's see how we can fix the history on disocclusion. So when we detect disocclusion, we drop most of the history. So not all, as it helps making the transition smoother. So we keep a small part of the history, creating some unnoticeable ghosting that we then integrate to this new disoccluded sample. Another way to improve the disocclusion quality is to blur the incoming sample. And this is done during the previously described upsampling stage at no additional cost. So instead of increasing beta, we decrease it to widen the length of curve and artificially increase the importance of all participating sample. And so this way we create a blurrier sample. So how about non-disoccluded cases? Accumulated color will drift, creating ghosting through imprecision or shading change. So the history color is still valuable information, but it needs to be fixed or fit into the new context, the new frame. So to achieve that, we do compute a validity range that the history color will be constrained to. This validity range is computing from a 3x3 kernel from a low resolution samples centered at the high resolution sample location. And this clamping is applied to the history color in the luminance-chrominance space. So if we look at this image there, we've got this 3x3 neighborhood holding effectively 4 different colors. So that's what is being plotted at in the middle picture. And from that, we can infer a clipping box. And the history to be rectified will be fit into that box. So another item that requires attention in temporal solutions is thin feature stability. So those features are triggered only a few times during the jitter sequence. Color rectification will take that feature down as soon as a new sample is coming in, and this thin feature is not part of this input signal. And that will usually result in unstable image or very dimmed features. For instance, pictorial highlights are very sensible to that kind of issues. So what you see on the left image, that's the zoomed in region of the right image. And you can see that the leg of the staircase handle there are barely visible. So how do we deal with that in FSR? So to solve that issue, we introduced a locking mechanism. We detect pixel size ridges and log them. Logged samples are now getting a spatial treatment in the color rectification stage. They will get a higher weight, so they are not taken down. On the 3 images there, you can see the same zoomed in region. And in the middle picture, you can see the locks that are helping stabilizing the right picture. So locks have been placed, and those need to be actualized, so they could get killed if the thin feature disappears. So to ensure that they don't live forever, the locks are being set with a lifetime that matches the jitter sequence length. The expectation is that the lock will be re-triggered when the matching jitter sample is re-rendered. This will make sure no lock stays. So to achieve the best result then, the jitter sequence length must be the shortest possible, still providing enough samples to achieve the expected anti-aliasing quality, that is the number of samples per pixel. So when the scene moves, or when there is a shading change, the locks might not be valid anymore and must be killed. Implicitly, killing locks through decay, as we proposed before, will most probably not be fast enough. And this will create some ghosting effects. So that's what you can see on the picture on the right, with the red dots being trailing locks that are still there while they should be killed because the context has changed through the disocclusion. The arm is moving and it's revealing something else that should not be locked anymore. So we need to detect and kill those. So to early kill stealth locks, FSR2 relies on disocclusions and shading change tracking. So on disocclusion, the lock is explicitly killed. If a new thin feature pops up in the disoccluded area, it is locked and it will be preserved for this frame. On shading change, the local low frequency new luminance is compared to the one at lock time. Past a defined threshold, the lock is killed. So the luminance filter there is only comparing low frequencies to purposefully exclude thin features that are high frequency. Switching topic a bit. So let's see how dynamic range data, high dynamic range data is being integrated into FSR. So a common artifact in temporal anti-aliasing solution is Firefly. And this is due to high-intensity samples dominating the accumulation result. And as for most temporal anti-aliasing solution, FSR2 relies on the local reversible tone mapping. So we rely on this one, the optimized reversible tone mapper for result that you can find on GPU Open. So the tone mapping is only applied internally, and it is fully transparent to the user. FSR2 input and output are then both non-tone mapped, always. And this HDR support is fully optional. You need to opt in to have those part of the pipeline. Another HDR related topic is about two additional parameters that are actually impacting the quality that FSR is able to provide. So the first one of those factors is the pre-exposure, and it's possibly used by game engines, and it actually affects the low resolution images that FSR2 then consumes. From the engine perspective, this pre-exposure value is usually cancelled out during tone mapping. So given that this pre-exposure value can change from frame to frame, FSR2 needs to be aware of that additional input so it can correctly mix images from different pre-exposure values. The exposure value itself now, this one is a per frame input too, and FSR2 uses that value to correctly align images to some common middle gray value. And this internally helps FSR2 to uniformly process images with different exposures. If the engine is not providing this input, an optional auto exposure stage can be enabled. And either this explicit value or the auto exposure stage needs to be enabled for FSR2 to achieve its optimal quality. Now, moving on to DRS. Dynamic resolution scaling is the ability for a game engine to adapt the rendering resolution to the current load of the game. Think of explosions with complex particle effects, for instance, that are possibly resulting in slowdown. One way to gain performances back is to render heavy scenes at lower resolution. Once the load decreases, the render resolution can be increased again. The final frame must obviously still be of the same size. And FSR2 has been thought from the beginning to be dynamic resolution scaling compliant. It does most of its work from input data, no matter its resolution, and every data that need to persist between frames, such as locks, are stored at high resolution, And so those will still be valid no matter the input resolution changes. So as an example there, you have 3 frames that are the same scene rendered at 3 different resolutions and that are composed correctly into the final frame that you can see on the right. One last point with regard to FSR2 internals. So FSR2 is also proposing an optional sharpening stage, and this one can be enabled to emphasize features that have been otherwise softened by the accumulation of low-resolution images. And this one relies on FSR1 RCAS. So in the 2 example images there, you've got on the left-hand side the unsharpened upscale image, and on the right-hand side the same one with some strong sharpening being applied. So that's it for the algorithmic walkthrough. So now I will be handing this over to Colin, who will now take us through optimizations that have been implemented. Thanks.
Thanks, Thomas. During the research and development phase of FSR 2.0, we worked on optimization passes to make the various compute workloads finish quicker. I will now talk about some of them that ended up giving significant gains on RDNA2 at various stages of development. One of the more obvious optimizations we performed was a review of the tone mapping operations that happen internally during the various FSR 2.0 passes. We do a reversible tone map at various places as it can improve the output quality. What this means, though, is a naive implementation could perform these operations per sample rather than per pixel. We do various neighbourhood samples during FSR 2.0, so the amount of ALU taken up in the tone map operations can quickly get out of hand. We worked to remove many operations which were not required. This means that we were able to keep tone map operations very close to per pixel output, opening up GPU resources for use by other operations within the workload. Another optimization we implemented aims to increase cache hit rates, and it's dubbed cache blocking. In a 4K scene, we can see quite a bit of read data, so much that the hit rates for caches can be low. On RDNA2 with infinity cache, there can also be some spilling, which leads to reductions in performance. To mitigate this, we can learn from how tiled GPU architectures operate. By splitting a single large compute dispatch into several smaller dispatches that all work on a local area of input memory resources, cache hit rates should increase. This is because workloads in flight from non-local areas of the input will not be causing cache lines to be evicted in favour of the non-localized reads, similar to cache thrashing. With higher cache hit rates, we should expect the memory-bound aspects of the workload to complete in a shorter period of time. Looking at the results in Radeon GPU Profiler, we see that this is indeed the case. The workload completes in less time, and the L0 cache hit rate has increased some 37% with splitting into 3 blocks. The number of blocks to split could be tuned for whatever GPU is currently running the workload, which is ideal for cross-GPU optimization portability. FSR 2.0 needs to know the exposure of the input, and as such, we provide an option which will automatically calculate the input exposure. Exposure workloads can be quite inefficient if implemented poorly, with a single thread compute dispatch or a pixel shader workload into a 1x1 render target. These are seen often, leaving the GPU underutilized. For FSR 2.0, we use the FidelityFX Single Pass Downsampler, or SPD. This compute shader solution is typically used for generation of multiple MIP levels at once very quickly. However, SPD has a configurable kernel and so can be modified to, instead of calculating a MIP chain, to only output the final 1x1 value, with the value being the exposure of the image. With SBD, the operation is incredibly fast, allowing the auto exposure feature to have minimal overhead. As mentioned by Thomas earlier, FSR 2.0 also makes use of Langshos and sampling logic. Traditional Langshos weights can be quite expensive to calculate due to the required transcendental operations being slower to execute on some GPUs. However, we also use an optimized Langshos approximation in FSR1 and can leverage that approximation logic for FSR 2.0. With this approximation, we reduce the ALU pressure in one of the FSR 2.0 passes, which make use of Langshos, resulting in some compute dispatches completing faster. We also have a secondary optimization for some RDNA2 architectures in this area, whereby we store pre-computed Langshos lookup tables in a texture and then sample it at runtime. With RDNA, Radeon GPUs were able to run workloads in two modes, Wave32 or Wave64. This was a significant change from GCN, where Wave64 was the only mode. Wave32 is found to be faster in many situations due to reduced latencies, but Wave64 can still win out in certain circumstances, such as using wave atomics or to better exploit data access patterns. By default, the FSR 2.0 compute shaders ran in Wave32 mode. We performed experiments and found that some FSR 2.0 workloads worked better with Wave64. As seen from this RGP event screenshot, many of the workloads ran faster in Wave64 mode. In fact, forcing Wave64 reduced runtime of the entire FSR 2.0 pass by nearly 12% on an AMD Radeon RX 6800 XT GPU. With shader model 6.6, developers can specify a preferred wave size at the source level by including a wave size attribute on the entry function of the shader. Now, this is only scratching the surface of the optimizations that were put into FSR 2.0, and in fact, some of them I detail here have been superseded by other work. Once FSR 2.0 source code is released, please feel free to go digging through the code to see what made the final cut. The last thing I'd like to talk about with regard to optimizations is fallbacks. Being cross-platform is a core GPU open philosophy, and as such, we want to make FSR 2.0 run the best it can on a wide range of hardware. However, some of the RDNA2 optimizations previously mentioned actually make some GPUs run slower. This includes previous Radeon products. What we do is mark optimizations in this category and ensure they have a fallback implementation present so the optimization is not enabled on certain GPUs. An example here is the wave size operation. It's only enabled for the GPUs where we see performance uplift with it enabled. The important thing to take from this is if you integrate FSR 2.0 to our recommendations, a set of optimizations will be used automatically. We have hundreds of permutations of our FSR 2.0 shaders to select from to ensure the performance we expect. And with that, it's now time to see how much FSR 2.0 costs in terms of frame time. As you can see, FSR 2.0 is incredibly fast. Remember, this replaces any existing TAA, and I have personally seen TAA passes alone without high quality upscaling perform around the numbers you see here. These figures here are from an early beta version that was provided to early adoption partners and is subject to change. Looking at a target resolution to GPU matchup, even with the best quality mode, you will be looking at upscaling with excellent performance characteristics, with the FSR 2.0 pass coming in at close to or under a millisecond per frame. With FSR 2.0, the quality mode has a small impact on the length of the pass, but will give a larger benefit over the entire frame. With the performance preset, which is a 2 times upscale factor, we see that the AMD Radeon RX 6800 XT upscales from 1080p to 4K in less than 1 millisecond. An AMD Radeon RX 6700 XT manages a 720p to 1440p upscale in less than 700 microseconds. With our performance and mainstream tier GPUs, like the AMD Radeon RX 6700 XT and previous generation AMD Radeon RX 5700 XT, gaming at the next resolution up is possible using FSR 2.0. I now want to talk about how FSR 2.0 can be integrated into games in the way we recommend for both the best quality output and fastest execution performance. FSR 2.0 will run in a wide range of hardware, including previous architectures using no dedicated machine learning hardware. Samples are provided for DirectX 12 and Vulkan, and a plugin for Unreal Engine will be provided. And for those interested in console development, a GDC sample will be made available to registered Xbox developers. We want you to be able to port without restriction to any platform of your choice. As explained by Thomas in the algorithm section of this presentation, FSR 2.0 has many more workloads and resources in play. The data flow is complex, and due to this, we have worked on a library and API that allows easier integration into game titles. The FSR 2.0 API is offered through a Windows library which can be linked against during the build process of your game title. Full source code of this library is provided, so you can rebuild within your game if required. The library has various logic for deciding the best permutation of optimizations to apply for the compute workloads. The API has 3 main entry points for context creation, destruction, and dispatch, and a selection of helper functions for working out associated data such as correct perspective jitter. Contexts all work through a callback interface system, and we provide implementations of this interface for DirectX 12 and Vulkan. The API is designed to be simple to integrate for those who want to get started directly with DirectX 12 or Vulkan, but powerful for those who intend on an extensive integration with other engine subsystems. This allows the interface to integrate, for example, into existing engine resource management. In terms of how long an integration should take, it will vary with the circumstances presented. However, as a rough guide, we expect the quickest integration to come from games which already support existing temporal upscaling or Unreal titles integrating the FSR 2.0 plugin. Next, games that have support for decoupled render and display resolutions come into 2 categories, with games supporting TAA being quicker to integrate. Without TAA will take longer. Lastly, games that do not support decoupled resolutions or TAA or motion vectors will take the longest to integrate, taking weeks. As we mentioned TAA there, I want to clarify just how FSR 2.0 fits into an anti-aliased frame. FSR 2.0 should replace any temporal anti-aliasing pass in the game frame completely. So when FSR 2.0 is enabled, TAA should not be run. However, if FSR 2.0 is disabled, then a TAA pass should be run in its place. We are developing an FSR 2.0 TAA only mode without the upscaling component, and more information on that will be available in the future. This will make the decision of when to run a TAA pass much easier. FSR 2.0 requires careful placement within the game render pipeline. As it replaces TAA, it is earlier in the frame pipeline than when compared to FSR 1. Post-processing that requires an anti-aliased input will need to be post-upscale, and any post-process effect that requires the depth buffer will need to be pre-upscale. Using the library requires 3 buffers be provided at render resolution at the time of FSR 2.0 dispatch. Internally, the FSR 2.0 library maintains output history buffers, so you do not need to implement any temporal loop logic. The input depth has various characteristics that can affect output quality, so we recommend that it is configured as an infinite far plane in reverse depth. The type should be R32 float. This will provide the best quality. However, alternate depth configurations can be used at the expense of possible lower quality. The flags are provided in the context create API, and there is one for inverted depth selection and another for infinite depth selection. The motion vectors should be provided as a single resource expressing 2D vectors in UV space. Please ensure the format is at least FP16, as 8-bit will not give sufficient precision, and internally all computations with motion are performed in FP16. It is very important to ensure that all scene elements are included in the motion vector resource, including items such as grasses. Like with the depth input, there are flags on context create which can be set to configure the motion vector resource for stating if the motion vectors have jitter applied and whether the motion vectors are at full display resolution. We understand that some games pack motion vectors into render targets with other data. If this is the case, you can modify the HLSL source in a single place to include the motion vector decode functionality and then otherwise use the API as expected. Now for input color. For low dynamic range pipelines, we recommend it is supplied in linear format. For high dynamic range, the input needs to be linear RGB. PQ or HLG are not suitable. Negative color input should always be avoided, as the input is clamped. If the input is HDR, a flag is required to be set on context creation. As briefly mentioned in the optimization section, the algorithm needs exposure information for the color input, and this can be handled by FSR 2.0 internally if the enable auto exposure flag is present on context create. If you already have exposure information, a resource can be provided through an FSR 2.0 API instead of relying on the auto exposure feature. As FSR 2.0 is a temporal algorithm, the scene needs jittered each frame to allow for the detail to accumulate. Our recommended perspective jitter is 0.523, and there are helper functions included within the FSR 2.0 library to assist with generating the correct jitter. An important thing to note is the sequence length, which depends on the scaling ratio. To ensure correctness, use the FSR2 getJitterPhaseCount function to get this length. This leads us on to dynamic resolution situations, where the scaling factor can change from frame to frame. Here, we need to enable the dynamic resolution flag and take care with the jitter pattern sequence length. Adjust the sequence length each frame to correctly reflect any change to the scale factor, and always continue the current phase through this change as seen in the timeline diagram here. This will then lead to the correct jitter being applied and maximize image quality by allowing the correct number of frames before sequences repeat, increasing the detail that is accumulated into the output. MIP bias is required when upscaling because the lower render resolution can result in images lower down the MIP chain being selected during rendering. The MIP bias allows us to ensure texture MIPs are requested at the same level as they would have been at display render resolution. The table here and associated function shows the expected MIP bias amount for the FSR 2.0 quality modes. One thing to watch out for is textures featuring high frequency details. An example is shown here from our Cauldron Sponza scene. This woven cloth texture should have its MIP bias tuned towards 0, as otherwise we may be able to see shimmering caused by temporal aliasing. FSR 2.0 includes an optional sharpening step with RCAS. It's performed as part of the FSR 2.0 library, so any existing RCAS pass in the graphics pipeline should be disabled when FSR 2.0 is active. The sharpness factor, unlike in FSR 1, goes from 0 to 1, with 1 being the most sharp. The FSR 2.0 API exposes a reset boolean, which is used to indicate that previous history is invalid and should be discarded. This is very important to use when harsh visual transitions exist, such as going between gameplay and cinematics. If reset is not used, some ghosting of the existing scene may present, so when integrating FSR 2.0, please ensure this is correctly handled for the sharpest graphical experience. This integration overview is focused on the library and API, but as FSR 2.0 is open source, it is possible to rebuild and integrate it manually into your game engine. This could be particularly useful for developers who use some sort of packed buffer or motion vectors and other color resources, and require the shaders to use custom decode operations. Please let us know if there are any feature requests in this area, as we want FSR 2.0 to be as easy as possible to integrate. AMD GPU Open has a portal detailing all the latest guidance on FSR 2.0 user interface, options, and language recommendations. We would appreciate FSR 2.0 being exposed in options menus using the language and quality modes as described. For more information, visit gpuopen.com/FSR2. And with that, we are at the end of the presentation today. In conclusion, FidelityFX Super Resolution 2.0 is a significant leap in quality over FSR 1. Its new temporal algorithms provide excellent quality and are optimized for extremely high performance. As seen in the zoomed in images here, FSR 2.0 dramatically increases edge quality and visual clarity. It's released as a library, exposing an API making integration simple for games which already have TAA render paths. It's open source, compatible on a wide set of graphics hardware without any dependency on machine learning, and will be released on AMD GPU Open. So please ensure you follow us on Twitter at GPU Open. As with any large software project, many engineers come together to make FSR 2.0 possible, and we thank them all for their contributions. And lastly, if you have any further questions, please do not hesitate to reach out to your local AMD representatives. We cannot wait to see your games full of high fidelity graphics running at high frame rates and high resolutions with FidelityFX Super Resolution 2.0. Thank you for listening.